Continue from previous video where we take the example again. Now we are taking similar example here. After confirming that section is compact, determining the design moment capacity of a 1000 WB, that is a welded beam 215 bent about its strong axis and with full lateral restraints. Now we are going to follow the same procedures as in the last video. We first find the plate element slenderness lambda e and the dimension of 1000 WB 215. So that is just a 215 welded beam are given below. So that information is extracted from the one steel tables, as if I'm going to show it here. That is that value are given here. If I can show it here in the hundred thousands WB 215 on page number 10 of one steel tables. We have a value of D 1000s, that is 1000 millimeter, BF 300 millimeters, TF 20 millimeters, and TW 16 millimeters. So that is the depth of the whole steel beams, width of the flange, thickness of the flange, thickness of the web, and D1 is the 960. So that is D1 is 960. That is just the depth of the web that is on the one steel tables. Now we can also demonstrate this one on the figures, like 1000 millimeter depth, width of the flange is 300 millimeter, thickness of the flange is 20 millimeters here, thickness of the web 16 millimeters, and D1 960 millimeters. Now let's work out the flange first, where we are going to calculate the B, which is the clear width, with BF minus TW on 2, and you substitute those value. 300 take away 60, 300 take away 60. Basically we are doing this one. What we are doing it, we are finding B. So BF divided by 2, you can say BF divided by 2, take away TW. So we just first find this one, take away, so this is TW divided by 2, and this is let's say BF divided by 2 to find these values. Okay, so that's 142 millimeters. Is easy from that can be easily seen from the pictures. Now T is a TF that we need to know in these equations. We need to find T, and that is in the picture here. That is the thickness of the flange, that is 20 millimeters, and Fy 300 millimeters. So if you turn it over here, and for the flange we have a here 215 1000 WB 215, that is the Fy for flange is 300 millimeters. So that is 300 millimeter from one steel table on page number let's say on 11 on the next page. Now once we have those values, now I need to add some here, because I think we done some calculations here. We can just exclude those calculations here that we done it in the just previous step. What I'm trying to say here, that when you do the calculation for the, let's say, flange, we can easily find this B over T ratio from one steel tables. How? I'm going to show it here. So let's do it here. 142 divided by 60, it give us 142 divided by 20, it give us 7.1. So these values given 7.1. Now how we can extract this one? Let's look at here. That is here 1000 WB 215. Basically we are looking for this small outstand here, which is BF minus TW on 2, and then divided by thickness of flange, that is 7.10. So we can extract this 7.10 straight away from the one steel tables that you can see here. So you can reduce that one. So we can find 142 divided by 20 from the one steel tables, and those substitute the value. Now we need to work for the lambda EP and lambda Vy, plasticity limits and the yield limits, same like in the last example. For the case of flange, we are using the table 5.2 on page number 51. We have a uniform compression hot roll sections. So for the case of flange, we have under uniform hot roll sections, lambda EP equal to 9 and lambda EY equal to 16. So lambda equal to 9 and lambda ey equal to 16. Now we have calculated lambda is 7.8, which is less than 9. So in that case, if it is less than 9, compact section between 9 and 16 is a non-compact section, above 16 is a slender section. So we can see 7.8 is less than 9, so we can classify flange is compact. That is given in the clause 5.2.3. if you just check it on page number 51, we have these compact sections where it's written here that lambda e value, lambda s value should be less than lambda sp value. That is the case for flange. Now let's work it out for the wave. Now for the case of wave, we have a this b and t. Again, this b over t ratio, which is 960 divided by 16 is 60. We can find it from the one still table. So that is 60. So that's value 410, and that is 60 here. That is a 60 here, d1 divided by dw. So that's 60 value, which is here for 1000 wb 250. So that's 60. We substitute here 60 times 300, so that is 60. We can say that is 60, and we can get it from one still table, or we can calculate using this one. And now fy for the wave, if you turn it the page over, there is a 1000 fy for the wave is given 300 megapascals for the wave for the 1000 wb 215. So that is 300 megapascals. Substitute here, that give us 65.7. Now again, we have a we need to find those lambda ep and lambda ey value. That is from the table 5.2 on page number 51. Now this fourth row, that's for the wave, and that is 82 for lambda ep and 115 for lambda ey. That's I written here. Now 65.7, that's what we found, 65.7, and that 65.7, if it is less than 82 is a compact. Between 82 and 115 non-compact, and greater than 115 is a slender. So by looking this number 65.7, which is less than 82, so the wave is compact. Now both flange and wave are compact, so the section classified as a compact. Now in the case of compact, we can find the section effective section modulus ZE by taking the minimum value of S and 1.5 Z. So we should in the clause 5.2.3 on page number 51, we have this information to calculate ZE, which is minimum of S and 1.5 Z. Now that minimum 1.5 Z, so S can be found it here. It's a strong axis, as I mentioned in the question. So Sx is 9570 and Zx is 8120. So that I substitute it. I substitute here 9570 10 to the 3 and 8120 10 to the 3. Please note about this 10 to the power 3 values that are for both Zx and Sx. We have 10 to the power 3 written on the top. Now once you substitute this S and Z values, we can find the minimum value between these two, which is 9570 times 10 to the power 3 millimeter cube. We have a nominal section moment capacity MS, that is taken from the clause 5.2.1 on page number 50. We have a nominal section moment capacity Fy times ZE. Now here Fy value is 300 for both the cases, like I can show it in the Australian standard, that 1000 WB 250, we have 300 for the both cases. Now that's 300 times ZE, we calculate 9570 10 to the 3, it gives us in Newton millimeters. So 2871 10 to the power 6 Newton millimeters, divide by 1000 for Newton millimeters, divide by 1000 kilonewton per meters. Now design section moment capacity, that equation is given in the clause 5.1 on page number 49. You can calculate this 5 msx or 5 msy for this design capacity 5 ms, which is 0.9 times 281. Now 0.9 is given on AS and ZS 4100 on page number 32 for members subjected to a bending with full lateral resistance, the phi value is given 0.9. So that phi value is 0.9 times by 287 give us value 2584 kilonewton meter. So 2584 kilonewton meter. So that's the answer for this example. Thank you.